Let me share the screen. Okay. And let me open this. Okay. So I go full screen and I welcome you to this webinar part of the Technical Talks of CTSoc series. So let me introduce myself. I'm Fabrizio Lamberti. I'm the Vice President of Technical Activities for Consumer Technology Society, CTSoc in brief. And today we'll have two speakers which are part of this series of talks which have been launched in the technical activities area of CTSoc. The technical activities area is one of the areas together with publications, conferences, industry and standard history in an IEEE society. And within the technical activities areas, we do have a future directions committee, which is in charge of identifying new areas of interest for the society and the technical committees. All the material that I will be presenting you is can be found on CTSoc website, and here you have the link, and then you will also find some QR codes. The technical activities area, as said, has been launched at the end of 2020, and since then we have established 15 technical committees. IoT was in the first batch, and QCT, the TC on quantum and consumer technology, has been launched more recently. But as you can see, Consumer Technology Society, which is basically the set of technologies that are used by people, and they typically have a limited cost and they're used by a mass, is covering basically the whole spectrum of technologies today. The technical activities area includes a technical committees board, which is chaired by myself. The vice chair is Dixon Lin. And here you have the names of the president, VP conferences, VP publication, VP industry and standard activities, those the VPs of CTSoc which are involved in this technical activities. Why? Basically because the technical activities are expected to be the engine, the core of the society itself. Here we have the names of the chair, vice chair, and secretaries of these technical committees. And please note that for many of them, the term will be expiring this year. So we will have elections for new positions to be appointed this year. Each TC has its own website, has its mission and objectives, have its list of members, have its license positions, and in case you or your colleagues are willing to become members, here there's the application form, the link, and the QR code to the application form for joining the technical committees. You don't need to be a member of IEEE or of CTSoc to be a member. This is a parallel or orthogonal community of people interested in these 15 areas. And as you can see, the areas are quite different in terms of size, but the number of members is growing month by month. What's the goal of the technical committees? Support CTSoc and its activities in all areas. And the areas are conferences, publications, standards, education, history, as I said. And what do I mean with supporting these areas? Well, some examples are the technical positions in conferences are expected to be identified, covered using people involved in the technical committees. When we launch a call for associate editor positions, we expect these people to be coming also from the technical committees. We expect these people to organize special sections in journal, sessions and workshops in conferences, be engaged in the cross-society initiatives that we are involved in too, as IEEE society, like the IEEE digital reality, digital privacy. We expect these people to be involved, and we involve with them in collaborations with other society like SPS, AES, These people launched special interest groups. We have one in the on the metaverse. They are expected to be selected as distinguished lecturers for webinar or the technical talks like this one. We launched funded projects in the past. They have been involved in the implementation of standards. This is an example of one of the initiatives that have been launched with other societies, published a platform to be used in IEEE conferences and also deployed as a standard. Other ways for getting involved is like serving in the conferences of the societies. And here I listed some of the conferences with open call for papers. The next ones, just four. So ICC Taiwan, ICC Berlin, a new conference, well, new in sense that it has just recently been announced, like GEM, Gaming, Entertainment and Media Conference, co-located with ICC Berlin and GCC in Kobe, Japan. But there are others, and you can reach us if you are interested. And let me just give you an overview also of the journal publications and ways in which you can be involved. Certainly, we have the transactions and consumer electronics and IEEE Consumer Electronic Magazine. Here you have the cover of this month edition. As you know, I'm serving as editor-in-chief, and I welcome you submitting special issues proposal. For instance, this one is a special issues on IoT. And there are currently 3 special issues open for submissions, and you see there, the call here, but just the summary titles and submission deadlines on the left. So we welcome you helping in these initiatives and also in the technical talks. And this is the long list of technical talks that have been organized over the last 2 years. Let me already say that the next webinar will be held on May 25th, same time, 2 p.m. Italy, Central European Standard Time. And also the next webinar will be participated by 2 speakers from 2 different technical committees. But without further ado, let me show you this picture, which is the one that we use for advertising today talks. We have 2 speakers today, as usual, Samaresh, Kumar, Singh from Hewlett-Packard, and Chiara Vercellino from Links Foundation. They represent 2 technical committees, the TC on Internet of Things, Internet of Everywhere, and Edge Computing, Samaresh, and the TC on Quantum and Consumer Technology, Chiara. So I'm really happy to have you here. I'm glad to listen to your presentations. I now would stop sharing and leave the floor to Dixon, who will kindly help with introducing you. And thanks, Dixon, for posting in the chat the link for joining as a TC
member. Thank you, Fabrizio. So it's my honor to introduce the first speaker. So the first speaker is from IoT TC, and Samaresh Kumar Singh is a principal engineering at HP company with over 21 years of experience in designing and building large-scale distributed systems, AI, machine learning platforms, and intelligent orchestration frameworks. He currently leads key initiatives in edge computing, including distributed AI systems, explainability frameworks, and scalable AI infrastructures. He is also an IEEE senior member and an active contributor to the research community with multiple publications in edge AI, distributed security, and agentic systems. His work focused on enabling real-time, trustworthy, and production-ready AI systems across industrial and IoT environments. And his title, today's title of his speech is Explainability-as-a-Service, enabling trust, transparency, and control in distributed edge AI systems. So let us enjoy his speech. Thank you.
Thank you, Dixon.
So I would like to leave the floor to Samaresh, please.
Thank you, Dixon. So let me share my screen first. And screen 2, share. So can you see my screen?
Yeah.
Yes,
Okay.
yes.
So good morning, good afternoon, everyone. First of all, I would like to thank IEEE CTSoc, the IoT Technical Committee, for the invitation. It's my real pleasure to be speaking with this community today. I'm Samaresh Singh, a principal engineer at HP. I'm located in United States. Today, I want to share some of the work on making explainable AI practical at scale on the edge. This presentation, in this talk, I'll be focusing on the idea from one of my research paper that has been published in IEEE Explore. I'll walk you through the core idea and results we are seeing across the real deployment. So let me go straight into this. Hold on. Okay. So here is the roadmap about my talk. First, I will talk about the motivation and problem statement. Then we'll talk about the problem formulation and system model. Then research gap contribution, how explainability as a service architecture looks like, what all core algorithm I have used, then experimental setup use case, finally results, and then limitation and future work. So AGI is everywhere nowadays, right? Uh, so industries like factories, hospital, autonomous vehicles, smart homes, all are growing, and a lot of new edge devices are coming in, right? So as of now, we have more than 100 billions of IoT devices connected across the internet, and that device will keep on increasing, and by end of this year, that number of IoT devices will go double or triple. So, with that comes as a real demand for transparency. A regulator wants it, user wants it, and honestly, all engineers, they want this explainability as a service for debugging their problem. So problem is that when you try to put classical XAI, explainability AI method, like Sharp or Lime onto the edge devices, the cost is really painful. So single Sharp explanation needs over thousands of model evaluation on Raspberry Pi. It takes seconds to execute a query. And here is the frustrating part, right? Similar input keeps coming in, and every new devices or every devices regenerate its own explanation from the scratch. So there is no way that we can reuse the existing explanation to serve the result to the user. So, yeah, and you can see that redundant computation will go more than redundant computation keeps on happening, and with the help of explainable AI, we can reduce that computation by 3 times, and there is no existing solution of caching exists today. So the key inefficiencies we can tell is the three. One is the redundant computation, resource matrix, and no reuse, because all the uh, all the query or explanation that all the query needs, the explanation needs to be regenerated. So that is the bigger problem nowadays. So let's talk about how we formalize the problem. On the left side of the screen, you can see our system model, a fleet of n edge devices, each with its own compute profile, bandwidth, and latency tolerance, plus a smaller number of edge server that can do heavier lifting work. Every explanation request comes with the fidelity threshold and the latency budget. On the right side, we can see the 4 validity conditions that have to hold before we can safely reuse the cached explanation. Without those condition meets, we cannot do that. The input has to be semantically close, prediction has to match, and model version has to be current or re-verified. So finally, fidelity has to meet whether a request is whatever the request is asking for. The key insight is the line at the bottom. You can see here. When all 4 condition holds true, then retrieving from the cache can save 2 to 3 times of the cost of generating the fresh explanation. This gap is where all our saving come from. So this is the research gap and contribution. On the left side, we see the research gap, no system-wide caching nowadays for explainable AI. Every request needs to regenerate the explanation. Second one is explainability AI methods are tightly coupled to the inference. So explainability AI runs on the same machine where inferencing inferencing result is generated, and they cannot be decoupled. No adaptive delivery by device capability and latency budget. No lightweight framework to manage the explanation lifecycle at the scale. And the last one is the stale explanation goes undetected after model retraining. So what happens that we have one model deployed and we keep on retraining those model over the time. So once the model gets retrained, all the explanation becomes stale, and those explanation remains undetected. So on the right side of the slide, you can see the XAS, what I have done in to achieve explainability as a service. So first is the cache. So this is a basically distributed explanation cache. Facebook AI semantic similarity search I have used. Semantic similarity index with the hit rate 72%. Then verify lightweight verification with 15 perturbations that detects 95% of the stale explanation. That is the current gap, and increases saves the cost by 3% of the SHAP analysis. Then we have a device-aware method like LAM, SHAP, or GradCam. Those are basically the explainable AI methods right now exist by capacity and latency budget, and then we we validated this result onto the manufacturing data from the manufacturing company, autonomous vehicles, healthcare, and we found that there was roughly about 40% of latency reduction and throughput more than 3 times. So here is the full architecture, how we can build explainability as a service. So this architecture can be divided into the 5 layers. First layer you can see is the IoT devices, where we have IoT sensors, smart camera, edge servers. Edge servers are really powerful. And then the request goes to the layer 2, that is called distributed explanation cache, right? So for any explainability request. So first, inference request goes to the second layer and it looks for that if that result is there in the cache, and if the cache hit occurs, then then verification happens on the layer 4 using the validity checker and fidelity checker. If there is a cache miss, then the explanation gets regenerated using the explainability AI in the layer 3. Three types of explainability AI we have: Line, Sharp, and GradCam. GradCam is for vision. Sharp is for text. And then finally, on the top layer, layer 5, we have service orchestrator, where the request comes in, and then that request gets load balanced by the load balancer. So going forward from here, we have 3 core algorithms that makes this architecture to work. First is the semantic caching on the left side. We embed the input using the domain encoder, clip for the image, but for the text. And then Facebook AI semantic search runs a near neighbor search over the cached embedding. We only accept a hit when all 4 validity condition holds true. Second one in the middle, you can see the lightweight verification. Instead of regenerating the full explanation to check whether the cached one is stale, we run only the 15 perturbations. That is about the 3% of what full SHAP computation would cost, and it catches over 95% of the invalid entries. Yeah, so basically this is a cheap and an effective one. Finally, the last one is the adaptive method selection. On the cache misses, we pick the both method and location, device, edge, or cloud. That minimizes the total time while meeting our fidelity requirement. It is a greedy search that is very fast to evaluate. So basically, to test this one, I have evaluation setup. These are the hardware I have used: the Raspberry Pi with 4 billion parameter, 4 GB memory to test the 4 billion parameter model. NVIDIA Jetson Nano, Intel NUC, and 5 Tesla T4 Edge server. So for the baseline, we use the 4 different models: local chain, cloud XAI, edge XAI, and fed XAI. Cache size we have is over 1,000 entry local, 10,000 entries global. That 10,000 entries cannot fit on the local devices, so use the cloud. Matrix edge-to-edge latency fidelity is over 90%, cache hit rate, throughput, and success rate. Then finally, protocol, 2 hours. So cache takes about 2 hours to warm up, plus we used that to run for 24 hours in 5 repetition each. On the right side, you can see the real world use cases where I have evaluated this model. First one is the manufacturing quality control, where 150 devices I have used. The 120,000 samples, 8 defect classes. Then autonomous vehicle fleet, where this has been run on 80 vehicles, 250K driving scenario, and then healthcare monitoring with on 200 patients, 89K vital sign samples. So here are the performance result. First of all, so on the left side, you can see the all 4 explainable AI. First one is explainable software as a service. That has, we observed that the latency, average latency of this one was 42 millisecond. Edge XAI has latency of 68 millisecond, Cloud XAI 95, and local gen of 127 millisecond. So key finding was, 30% in latency reduction versus the baseline model, that is the Edge XAI. More than 3 times increase in throughput versus local gen on the right side. On the right side of the bar chart, you can see here. And mean explanation fidelity is over 90% with 72% cache hit rate. So we cannot, our target was to achieve cache hit rate over, 80%, but it is really hard to do in the explainable AI. So this is the cache performance and scalability. So across the 3 industry, manufacturing, health, and automotive, you can see that, manufacturing and healthcare have a cache hit rate of over 70% or little over than that in 24 hours of testing. And automotive have little less, roughly about 68 or 69%. And cache takes 3 to 4 hours to warm up, and after that it becomes ready to serve. So scalability result, we can see the latency growth of 37% when we increase the devices by 100 times. Success rate under 300 requests per second under the peak load. And the bottom one, you can see the 300 requests per second, how the explainable AI is efficient, 97%, local gen is just 61%. So going next here is the limit. So we do have some limitation. So first one, as I discussed, is the cold start. So whenever so cache takes 2 to 4 hours time to warm up and becomes ready to serve. Second one is the model churn, frequent online update or frequent model update. If you are doing that, can thrashes the cache and degrades the cache reuse. Third one is the deployment, best fit for a stable model, a repetitive pattern, poor fit with less than 30% hit rate. A scope evaluated on the featured attribution methods, Lime, Sharp, and GradCam, as I said earlier. Here are the feature directions: federated X SAS, collaborative explanation cache across the federation, privacy preserving, counterfactual caching, and then continual learning. That with that we do incremental verification plus partial cache invalidation as the model drift. Then finally, security and privacy, different privacy and security multi-party compute for sensitive domain. So here are the conclusion and key takeaway. Service-oriented explainability as a system service. XSaaS decouples the inference from the explanation generation, treating XAI as the first-class citizen, distributed service like CDN or MLAS. 38% of latency reduction, more than three times of throughput using semantic caching, lightweight verification, and adaptive selection. Achieves this across the manufacturing, automotive, and healthcare deployment. Validation, over 95% still cache detection at just 3% of the cost. As you see here, the 15 perturbation we have used instead of thousands. Scalable and accountable auditable AGI. This is the foundation for scalable, transparent AGI across the heterogeneous IoT fleet. That closes the gap between XAI research and deployment reality. So so this is me. You can connect with me via LinkedIn. This is the GitHub. Please feel free to explore. I have a lot of projects there, including the current one. I have, and you will find, many, different projects and my source, open source contributions. On the right side, this is the link to access the entire research paper. You can take a look, and if you have any question, you can send me email or talk to me in LinkedIn. So yeah, finally, I would like to thank you everyone and open to take questions if someone have.
Thanks, Samaresh. I think the topic is really hot today. I will leave the floor to the with Dixon to the to potential questions. Is there any question for Samaresh?
If I may.
Hi, David. Sure.
Hey,
Maybe.
Samaresh, a very interesting talk. Thank you very much. Just a quick question on slide 10, the graph where you have the three domains. Do you have any insight as to why the automotive doesn't perform as well as, say, healthcare and manufacturing?
So in the automotive industry, the data changes more frequently than the manufacturing and healthcare. So the reason is in manufacturing we have cameras and most of those data are almost similar, right? But in automotive industry, what happens that when your automotive moves from the different area, different road, the data changes frequently, and that is in the motion, right? We collect the data in the motion. So it is really hard to match the accuracy as we got in manufacturing and healthcare because of those changing environment and motion of the vehicles.
Very good, very good. And just a quick follow-on question. In healthcare, what kind of data are you dealing with? Is it patient data or is it biometric data or?
Yeah, so basically the all visual data we collect from the patient room, from the emergency or some other places, and also we collect the data like his health report, like how was his health report and previous past and the current health state to evaluate the current health status. So most of those data are static, and some of the data we get feed from the healthcare service center, and some of the data we feed through the live streaming.
Very good. Thank you very much. Very well done.
Thank you. Any more questions?
I think that should we have more questions, we might ask them at the end. If everybody is okay, we can move to the next speaker. So to leave Chiara the expected time, and then if there are still questions both for Chiara and for Samaresh, we can take them at the end. Is that okay?
Yeah.
Yeah. Okay. So please, Dixon, I leave you the floor for introducing Chiara.
Okay, thank you.
And thanks again,
So,
of course, Samaresh, for your talk.
Okay, especially thanks for the Samaresh talk. So let us go to the next speaker. Chiara Vercellino. She holds an Master of Science in Mathematical Engineering from Politecnico di Torino. She is currently a PhD student in computer engineering and an expert researcher in the CPE, Advanced Computing, Photonics, and Electromagnetics area at Linux Foundation. Her research focused on optimization and machine learning algorithms, with particular emphasis on industrial application of quantum computing. She is actively involved in ETP4 HPC as a member of the SRA 7 working groups, quantum computing and mathematics and algorithms. She is an NGI Enrichers Fellow with the NISQ EMU project. which aims to design and implement NISQ-aware quantum error correction protocols for superconducting hardware. She also led and developed the QRISTIN project, quantum routines in space-terrestrial integrated networks, focusing on hybrid quantum classical algorithms for optimizing integrated satellite terrestrial communication networks. And her speech title is Hybrid Quantum Classical algorithms for next generation space terrestrial networks. So let us enjoy her speech. Thank you.
Thank you very much for this very kind
okay.
introduction. So I'm just sharing my screen. So this one here, this one here. Yeah. Okay. So thank you everyone for having me here today.
Can you go full screen? Yeah, perfect. Thank you. Sorry for interrupting you. Yeah.
No problem, no problem. Just a little bit of lag. So yeah, as mentioned before, like the title of my speech today is about hybrid quantum classical algorithms. Mostly this is because current state of quantum technologies does not allow us for have, let's say, fully quantum pipelines to tackle properly practical application. So today I will bring to you some insights from the Christine project. It was this project which was partnered by Links Foundation, so the research center where I'm from, and Chiara Computing. Chiara is a hardware provider, so they build a quantum processor units. Specifically, their hardware is based on neutral atoms, and we did together this project. The aim was to put together two very complex technologies. So on one side we had quantum computing, so the quantum computers, which in our case was like the tool to solve the problems. And on the other side, we had these space-terrestrial integrated networks. These are, let's say, a new technology, the space-terrestrial integrated networks, for short STINs, because they involve both the terrestrial component of communication networks, so the most known one, and satellites. Of course, as you can imagine, adding satellites to the network increases a lot the complexity of the corresponding overall network, because satellites move, so they don't have, let's say, a fixed coverage. Also, having satellites that moves changes the network topology continuously across time, but they can be a very relevant and useful added component, especially if we want to expand the service coverage of classical networks. And this is done particularly targeting the remote and underserved areas, which usually are not sufficiently covered by the terrestrial element. So in the Christine project, we addressed two main focus areas. So first, we had to model the STIN optimization problem, and this is just like a classical modeling of optimization problems. And then we had to develop a quantum-based algorithm that could find, let's say, a right place for quantum in this overall pipeline. So the main element in our application, our use case, are the terrestrial part of the network, so which consists in ground station and gateways, and satellites. Among satellites, we focus on LEO, so low Earth orbit satellites. So basically, the satellites which are closer to the Earth. This is done because there are more LEO satellites than other satellites at higher orbits, and they also enables a broader kind of communications. Among the hypotheses that define our problems, there is also the fact that we are not considering inter-satellite links, so satellites do not communicate directly with each other. We, of course, since we want to do an integrated network, we assume that visible space-to-ground communication, and we also assume dual mode terminals, so like user can either connect to satellites or to the terrestrial part of the network. The goal of the optimized network is, of course, to expand the network coverage, but also keep in mind a good balancing of traffic, and that is enabled through a proper gateway selections. And also, we want to reduce interference, so to provide to the users, the final users, the best services possible. So we want to assign frequency to the transmission path properly so that we reduce the interference phenomenon. And this is done, as I said before, in a very complex situation in which the topology of the network changes continuously in time. So now we need to do like a step back, because then we want to represent our problem. And since then we want to execute a quantum routine on the quantum computer, we need to model the problem properly so that it is kind of understandable for the quantum computer. And the key element is that this kind of networks can, as most networks, can be modeled as graphs. So we have nodes in the graph, which basically represents elements in the network. They could be satellites, they could be ground stations, they could be gateways. And we have edges, which represent feasible communication links. Given these graphs, then we can tackle a quantum optimization methods based on analog quantum computing, specifically on neutral atoms quantum machines, which are like those provided by Chiara, the partner in the project. Why we want to use this kind of machine? First of all, because among the current quantum computers, they offer quite a large number of qubits. The Aquila QPU, so Aquila is the name of the quantum machine of Chiara, has up to 256 qubits. Also, by arranging the qubits into the machine, you can represent different graphs. This is why we wanted to represent our problems through graphs. And this then enables, once we have represented the problem, the execution of hybrid quantum classical algorithm. So first step is to, let's say, refine a little bit the definition of the Stein optimization problems. Actually, we defined three subsequent optimization problems. The first one is satellite selection problem. Basically, given like an area of interest, we have the terrestrial network, and we have the satellites that could potentially cover that area. We simulate the orbit of those satellites and individuate those that can actually cover the area, and also individuate which satellites, let's say, have conflicts in the sense that they cover the same area for a large portion of it in the same time. So then we want to identify which are the best satellites to cover that area. Basically, we assign weights to each satellite corresponding to the portion of the area that they cover. And then we model the conflicts as edges in a graph. And so if we want to find the best weighted satellites, then we want to solve MWIS, maximum weight independent set problem. So we want to find non-conflictual satellites, so an independent set of satellites which has the maximum weight. So that covers the largest portion of the target area. Once we selected the satellites, then we can choose which are the best gateways. So which are the best gateways that would enable the integration between the terrestrial component and the satellite component. And this is basically a matching problem on a bipartite graphs, where on when some edges, some nodes of the graph, some vertices of it are satellites, and the other class in the bipartite graphs are gateways. And we want to match those as to balance as possible the assignment between gateways and satellites. And finally, once we have this overall structure, we want to optimize frequency assignment. So that is spectral assignment problem. And that is also modeled as another very common and well-known optimization problems in graph combinatorial optimization, which is graph coloring. Particularly suited for the neutral atom quantum machine, it is the first mentioned problem, so the satellite selection one. Because as I said, it is modeled as a maximum weighted dependence set problem, which is also defined here on the right side of the slide. And it is also the kind of problem that the neutral atoms quantum machine models natively by its own interaction models. So now we have, let's say, the formal definition of the problem. We know which kind of instrument we want to use, which is Aquila QPU. And then, but we still have to be able to represent the desired problem into the target QPU, because actually the kind of graph that we can represent onto the computer register have to respect some constraints. First of all, there are, let's say, requirements on the register, which it has a limited limited area, so we have to respect the register dimensions, which are reported here. But also qubits in the QPU are loaded by rows, and those rows, which are the positions of the atoms, must be spaced by at least 2 micrometers. And then we have also some requirements in the interatomic, on the minimum interatomic distance. Moreover, the kind of graph that are natively represented to the QPU machine are unit disk graphs, which means that there is an edge connecting the vertices, which are the qubits, only if they are closer enough, namely closer than the Rydberg radius, which is a characteristic distance of the machine. So when we want to represent the graph, we have to both take into account the requirements of the machine and the adjacency pattern we want to reflect in the graph. This is also a very complex problem, and so our solution is actually a neural network-based model, which is called here the DEN model, distance encoder network. So once we have been able to represent the graph into the QPU, then we can use a quantum algorithm to solve the corresponding NWS problem. This big formula reported here is the Hamiltonian of the problem. It describes how a system of qubits behaves, and it has a few parameters. You can see here the P-high vector. Those are the position of the atoms, so the position of the vertices in our embedded graph. And there is also the omega, which is the Rabi frequency, and in the plot below, it is the first pulse you can see. And then there is also the local detuning delta, which is instead the figure at the bottom of the slide. And that delta is side dependent. So each atom is heated by a different value of delta. And that enables representing the weights in the maximum weighted dependence set problem. And those poles have that specific shape because they represent an adiabatic process. So basically, at first we start with an easy initial state, which basically is all qubits in the ground state. Then we hit those with those adiabatic pulse, and at the end of the pulse, we have that our system basically represents a solution to the NWS problem. So I don't know if you're, let's say, familiar with that, but when we do quantum algorithms with samples, so we repeat the same path that's shown in the slide before several times. every time we measure, and every time we get that for each qubit, we have either a value of 0 or a value of 1. In our case, 0 value means that the corresponding qubits is the ground state, and so it is not selected as a solution in the NWS problem. So basically, all the ones are the vertices of the graph which are selected into the as a solution of the NWS problem. And we have different B-strings, so different solutions. And we want to obtain the best one. In this plot here, you see that before we do not apply post-processing, so we just keep those measures. But say with a very simple post-process, which basically means we do not consider solutions which are not visible, so they are not independent set, and we add vertices to the other solution up until they are maximal, so no more vertices can be added. Then we can enhance the presence of the best solution. In the first plots, it is emulation, so the quantum system is emulated through classical resources. In the last plot, instead, in a bottom plot, instead, it is actual QPU, so it is Aquila QPU measurements. And we can see that when we have moved to the actual hardware, we have the influence of noise. So the system is not perfectly quantum, and that say kind of worsen the solution at the end of the algorithm, but still we can retrieve the best solution. And this is the overall process done overall the instances of our SSP problem. And the x-axis is the size of the graphs. So we have up until 100 or so vertices in the graph. And on the y-axis, we have the relative improvement. The benchmark optimal is provided through a classical solver. It is a Gurobi solver. No, it's a GLPK solver. And we also use another solver, which is a grid heuristic, which basically selects iteratively the maximum weighted vertices up until we do not violate the independence constraints. And we can see that the quantum-enabled algorithm beats constantly the grid heuristic. It occasionally beats the classical solver up to the same computational time, but of course there is still it's still hard to beat classical solvers, so we might need some more experimentation on that, maybe some more advanced post-processing techniques. And yeah, that's all. I know, like I've said a lot of stuff, but if you're interested in any specific point or want to ask question, I'm here to answer. Otherwise, these are my contacts. Thank you.
Thank you, Chiara, for this very nice speech. I leave the floor to Dixon and the others in case they have questions, or anyway, if there are questions also for Samaresh.
Yes. Actually, I have one question. So, from Chiara. Question is, how do you decide which part of STIN optimization problem should be handled by the quantum routine versus classical method?
Okay, thank you for the question. Basically, it is in our case that the first problem was natively represented by the QPU, because when you find the ground state of that Hamiltonian I show you in the slide, you have that the corresponding solution is a maximum weighted dependence set problem if you have, let's say, represented the problem properly, and if you don't have, let's say, quantum noise effect. But and that is a good starting point. I know this very kind of different technologies from digital quantum computers, which are probably most known. Analog quantum computers do not offer, say, such flexibility. They are not universal machine. But let's see, looking at the kind of Hamiltonian that the machine provides can help you defining which kind of problems it is much more suitable to tackle.
Okay, yeah. So one more follow-up question. So what are the measurable advantage do you expect from that split?
The advantages, sorry.
Yeah, measurable advantages you expect from that split.
Basically, the idea is that this kind of quantum machine, as you scale up qubits, so basically as you can scale up with also the size of the problems that you can represent, they solve the same problem in a constant or almost constant computational time. Whilst instead, classical solvers usually, as you start growing up with size of the problem, you start not being able to retrieve optimal or feasible solutions. So it is much more a thing in prospect. Right now, of course, we don't have a machine which have, say, such large qubit counts that enables an actual advantage. But at scale, there is some prospect on that.
Yeah, thank you so much.
Welcome.
Other questions?
Yes, I have a question for the Samaresh speech. Okay, so when we do the healthcare AI models, we have to consider the security because the privacy of is very important. So if we just add some error correction code to protect the weight of the AI models, does your model can work?
Yeah.
Because I think the transparency may be affected by doing some protection of the AI models.
Yes. So basically, we are providing the protection through the infrastructure. So everything runs on the edge, not on the cloud. So everything is in the hospital premises where the IoT server will be set up, IoT devices will be set up. So it will be running on. So all the explainable AI and inferencing will be running, on the same infrastructure, but in different places. So that is how we provide the security. It never leaves the infrastructure, first thing. And then the another one is through the TLS TLS 1.3 communication, and all the traffic will be encrypted because we need to send some of the filtered metadata to retrain the model, right? So that all will be sent through the secure communication channel, and the traffic will be 100% encrypted. So that is how the security we provide. All the data in REST will be also encrypted, so that if someone tries to intrude into the IoT devices, they won't be able to decrypt the information.
Okay.
Thank you.
So thanks for the questions. Thanks again to our speakers, Samaresh, Chiara, for shedding some lights on this explainable AI and AI at the edge on the one side, and quantum, definitely inspiring topics for me and for everyone, I hope. I hope that you enjoyed these talks. Next talk is already planned, will take place on May 25th. So I invite you to join. And thanks again, Chiara, Samaresh, Dixon, and all the TC officers and you who chose to stay with us together. The webinar will be also published online, and I will get in touch with the speaker in the future for other collaborations. So thank you and bye-bye.
Thank you, Fabrizio.
Thank you.
Thank you.
So much.
Bye-bye,
Bye.
everyone. Bye-bye.
Bye-bye.
Bye-bye. Thank you.
Bye-bye.
Bye-bye.
Thank you.